All right, so first unit, first lesson of advanced functions. This is power functions. A couple things that I just want you guys to sort of note that you will see on every lesson as well is what we call learning goals. And the learning goals, I mean, it's sort of something that I have to have in my documentation, but it's also for you guys as well. So it gives you an overview of, by the end of this lesson, I should be able to, I should know, and I should understand these things. So I think of these lists as like really good as like just self-reflection lists. Once I get to the end of that lesson or worksheet, I'm going to go back to that list, or maybe even when I'm studying for a test, I'll go back to each of those lists and I'll be like, okay, do I know the difference between a polynomial function and the difference between something like a different type of function, like a square root or an exponential function or whatever? And then I'll be like, yeah, I do. So I'll check that off. Can I determine the degree and leading coefficient of a polynomial? Yeah, I can do that. So that's sort of like a good way to understand what the highlights are from that lesson and what I should come away with. So I would encourage you guys to use that as just a checklist. Okay, let's get into it. We're going to talk about some basic graph shapes. Some of these things may be graphs that we've looked at in grade 11. This one is not something that you may have seen before, but let's talk about y equals square root of x. This is a function that was introduced to us in grade 11 in the transformations unit. Can anyone show me, like with their hand, what this function looks like? You guys can just do it. Trent, yeah, perfect. That one's exponential, so this versus this. So this one starts at 0, 0, and it's almost like a quadratic that's like on its side, and then half of it's like erased out. Okay, so we call this square root function, or sometimes like we called square roots last year radicals, so sometimes we could call this like a radical function. Okay, 1 over x. Does anyone remember this? You can just show me with your hands again. What was that one?
Like this?
Yeah, yeah. So it has like two pieces to it that are sort of like diagonally symmetrical. This is that one that had those like asymptotes as well. So it had those invisible lines that our graph doesn't cross or doesn't touch. And then it has those two diagonal pieces that are sort of symmetrical. And we call this a rational function. Rational meaning like fraction. And y equals, so we didn't learn what this function actually looks like on a graph, but I think in my classes at least, we talked about these like bars. Does anyone remember what these like bars do? Carol? It's absolute value. Do you remember what it does? Yes, so everything's above the y-axis, and what would happen to any number that I put in there? Oscar? Makes every number positive. So I want you to think about this for a second. You don't have to write this down. But y equals x. What does that look like? This is like the most basic function that we started learning in grade 9. Mathushini? Yep. So this is the most basic line where all the y's equal the x's, right? It's a diagonal line. Now, if I changed it to absolute value, if I put any negative x's in here, it's going to make them all positive. So it's going to give me all positive y's out of that. So instead of having this negative section here, it actually gets flipped up to the positive section. And we end up with this function that's like a v, like so. Okay, so that's what our absolute value function looks like. Okay. We also, as Mathushini said, we also have learned about the line in grade 9, so that's pretty self-explanatory. Grade 10, what was our grade 10 course like all focused on? Learned about like one function in grade 10 for like half the year. Lucas? That was grade 9, so that's your line. Jess? Parabolas. So you've got like your U-shaped graphs. So that would be like another basic graph shape. So these three right here are not power functions. These are other functions. Oliver did the shape of an exponential function. We did that last year as well. So exponentials, they start small and get really big, or they do the opposite, right? They start big and get really small. These ones below are power functions, and you'll notice that all of these are like a y equals x to some exponent. So that's sort of how we can recognize them. So actually, the line that we talked about above, before we made it an absolute value, is the y equals x line, which is just a regular standard line. It's the simplest line that we can have, where we basically just have all the x's equaling the y's. So we have points of -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and so on. So we call this a linear function, and the graph shape itself would be called a line. Okay, y equals x squared, this is like what our grade 10 year sort of focused around. We did like intersections of lines, quadratics, and trig. So the quadratic, the most basic quadratic that we can have is just like this quadratic that is at 0, 0, it's symmetrical. So we call this function a quadratic function, and the graph shape is called a parabola. Okay, then we're going to get into some stuff that we haven't talked about before. Does anyone, just out of curiosity, know what y equals x cubed looks like? Yep. So Mathshini's got it. She says something like this. So it's almost like similar to the line, but as if it was like just curved a little bit. So what ends up happening is when we take all the x's and we cube them, we sort of get that like curved shape that ends up looking like this. And we call this a cubic function. There's no like official name for the graph shape like there is for the line and the parabola, but this is cubic. Okay. So I wouldn't expect you guys to necessarily know that one because we haven't talked about that before. Same with all the rest of them. So I want to show you guys x to the 4 on Desmos. And I think many of you guys have probably done like projects on Desmos before. If you haven't used Desmos, it's just a really easy graphing resource. So if you ever want to see what a function looks like or check an answer or something like that of a graph, I would recommend this. There's also an app that you can get. So here's y equals x to the 4. This looks very similar to, I don't know if that, oh, there we go. Okay, it did work. Okay, so this looks very similar to our quadratic function, right? Sorry, let me put this on projector mode for you guys here. So here's our quadratic. This one's our x to the 4. What do you notice about this one? What are the differences? There we go. Okay. What are the differences here between each of these functions? Oliver?
Y equals x 4 is like y to the 8, but it's 2/5.
Yeah, so it's like a little bit like skinnier, but also has like a bit more of like a, it's almost like a little bit more squared, right? So super similar, but just like slightly different. So this guy, we'll just try to draw it like a little bit skinnier and maybe like a bit more with like a squared base versus, I'm going to do a bad job of this, but there we go. Okay, and this is called Quintic. Another way that we might say something like this would be degree 4, because it has a 4 exponent. Okay, we'll get into the idea of degree in a couple minutes here after our break. Okay, so if this happened between x squared and x to the 4, does anyone have a prediction for x to the 5? What might this look like? Remind me of your name, sorry, Alicia. Okay, will it look like this? Okay, So skinnier is correct. Lucas?
Will it be similar to x cubed?
It will be similar to x cubed. So if we notice this is x squared, and then we jumped to this shape, and then this is the x4, and we're kind of back to that U shape. So it's going to look skinnier, as Alicia said. It's going to have that S shape. And it's also going to get like a bit boxier too as we go. I know it's your break. So we'll just do the picture of this quickly, and then we will finish the rest of this when we get back. Okay, so a bit skinnier, a bit boxier. And this is called quintic. Okay, or we would refer to this as like degree 5 because it has exponent 5. Okay, let's pick this up after our break. I will see you guys back at 10:15. All right, so we left off on quintic. This looks similar to a cubic. Any predictions as to what x to the 6 might look like based on sort of maybe some patterns that we see emerging here? Oliver?
I'm going to guess go even wider base than y equals x4 and then steeper.
Okay, so steeper or maybe like skinnier this way, and then maybe like a little bit more boxy at the bottom. So why don't we just add that right onto this graph here? We'll go y equals x to the 6. And if we sort of look at the difference, this is x squared, and then we've got x to the 4. Let's just zoom in here a little bit. Oh, sorry guys. Thanks. So this is x to the 4 in red and x to the 6. And then if we add in x to the 2 here, we can sort of see the difference. So it becomes like, it's very similar, right? It becomes like the slightest bit more boxy and then like a tiny, tiny bit like stretched more, but very similar in shape. So we'll sort of draw something that's like very similar to our quartic over here. Okay, and sometimes we call this like hexic. Once we get like to these high of degrees, like sometimes again we'll just yeah, so sometimes we'll call it like hexic, but by the time we get to degrees this high, like we'll literally just usually refer to it as like, we would say like degree 6 because it has exponent 6. But if you want to list the name hexic, we will literally probably never use that again. But yeah, we'll just start referring to things by like, okay, this is degree 6 or degree 5 or 7 or whatever. Okay, so what might happen, like we're not going to draw it because I think we can sort of start to see the pattern that's emerging, but what might happen if we did y equals x to the 7? What might this look like? Athena?
It would look like x5 is x to the 5, but skinnier and like more squared.
Yeah, so just to reiterate, it will look like y equals x to the 5, but stretched a little bit more or skinnier a little bit more, and it will be like a bit more boxy, as we've sort of been noticing. So all of these 6, and then if we continue with the exponents, x to the 7, x to the 8, x to the 9, and so on, all of these are what we call power functions. These functions take the form y equals x to some exponent, so we'll call that exponent n as a placeholder. And it has some specific criteria about the exponent. Firstly, the exponent has to be greater than 0. So it must be positive, and it's not equal to 0. And then also we would say and where n is from the set of integers. So the way that we say that is n, and then we'll use this little e, which means is a part of the set, or we'll say it could mean like is an element of. And then this is the set of integers. So it's like a z with a double bar on it. So I'll just put set of integers. What is an integer? Whole number. Integers can technically be positive or negative as well, which is why we have this stipulation that n must be greater than 0. So in other words, what we're saying is for something to be a power function, it is y equals a single x to some exponent, and that exponent must be positive and whole. That's what we're saying kind of like in math language here. So essentially it's just the counting numbers, right? Like what I learned when I'm like, I don't know, 2 or 3, I start to learn how to count. I'll say 1, 2, 3, 4, and so on. So that's essentially what we're talking about as far as the exponent here, just the numbers that you would normally count, positive whole. Okay, so with what we learned above, you should be noticing that based on what we would say the degree is, so the number of the exponent, some of these are even and some of these are odd. What is the trend with all of the even graphs here? What shape are they taking on? Nicole? Okay, so we would say the even graphs are, did you want to add to that?
It's a parabolic shape.
Parabolic shape, or we can even just say U-shaped, right? And then the odd ones, with the exception of this one, just because this is a line, but as we go higher in the odd ones, we would call these an S shape. Okay? So evens, we're noticing that all of these are taking on a U shape. Oops. And then odds, all of these will take on an S shape. Okay, and when I say even and odd, I'm talking about the exponents. So even exponent versus odd exponent. The bases will always be x. So just so we are confident in determining between like a non-power function and a power function or polynomial function, which we're going to go into next, if I have something that does not have a base of x to begin with, that will not be a power function. So if I had something like 2 to the x, this is not a power function, right? Because x is not the base, and I don't have a whole positive number as the exponent. This is an exponential function, actually. Same with y equals root x. That does not have a whole number exponent, so that would not be a power function. Same with 1 over x. It needs to be just x to some whole number, whole positive number exponent, okay, to be a power function. So just so we know. Okay, so power functions lead us into this thing called a polynomial function. We have talked about some polynomials before. We've talked about binomials in grade 10 and 11, and we've talked about trinomials in grade 11 and 10 as well. Poly, meaning many. So poly is many. And nomial meaning term. Or terms. So when I say binomial, what is a binomial? Does anyone know or remember? Remind me of your name one more time. Alicia, never mind. Got it. 2. Binomial, bi meaning 2, 2, and then nomial meaning term, 2-term expression. X plus 3, something like that. How about trinomial? 3-term expression. So trinomials, we did like trinomial factoring, like our ax squared plus bx plus c. So those are actually both considered polynomials. So it could have one term or it could have more, right? So this guy right here looks a little bit scary right now, but don't worry, it's not super scary. So polynomial, when we move from power functions into polynomial functions, they will be multi-term expressions rather than just like y equals x to the 2 or whatever. I could say as well, this is still a polynomial, it's just a monomial, right? It's one term rather than like more than that. So power functions fall under the umbrella of polynomials. We can still call these polynomials. But if it's a power function, it would just have the one term. Once we get into polynomials, we can have one or more terms in that expression. So a couple things about polynomials is we'll start to refer to polynomials as degree n. And n will be the highest exponent on an x that we see. So this one here will look for the x with the highest exponent. Even if I have x's with other exponents, I will say that the x with the highest exponent, let's say it's x to the 4, I would call that degree 4, okay? So polynomial has degree n. with coefficients, and these are just all representing numbers. So these just represent all our different coefficients. So an, the next one in the list, an minus 1, all the way down to a to the 1. So again, if this doesn't make sense right now, it will sort of make sense once we do an actual numerical example. And then we have this thing called a leading coefficient. And as soon as I find the x with the highest exponent, the leading coefficient will be actually the number that is found in front of that x with the highest exponent. So this is our leading coefficient, provided that our polynomial is arranged with the x's in descending order of exponents. So I want to have, like, ideally, if I were in grade 10, let's say, and I were expressing a trinomial, I would express that trinomial with my x squared first, and then I would express it with my x next, and then I would express it with the constant after that. So I express the x with the highest exponent, and then the x, and then the constant. So same thing with all other polynomials. If it's in proper format, it should be expressed with the x exponents in descending order. Okay, so when I look for leading coefficient, I just want to make sure I find the x with the highest exponent, and then I look in front of that. Okay, we'll do examples in a second. So our leading coefficient will be an. And notice that I did not include a to the 0, or a with the subscript of 0 in this list, because that's not a coefficient, it's a constant term. So it doesn't have an x with it. Okay, so our constant term is a with the subscript of 0. Okay, and I can identify the constant if it has no x with it. Okay, so with all of that, with some of that like math language in there, let's actually just look at a numerical example here and put this all together. Okay, so we're going to state degree for this. We're going to state leading coefficient. We will do the constant. Basic shape, so either U or S shape based on what we say the degree is. Okay, so I'm going to look through all the x's. Question? Oh, answer? Okay, give me 1 second. Or were you stretching? Okay. Okay, 1 sec. So we're going to look through all of the x's, find the one with the highest exponent. That exponent is your degree. So Oscar, what would that be? Okay, so this one would be 4. So if I look through all the x's, I'm finding that this one has the highest, so it's the 4. I get that it has a 3 in it too, but the degree is what's going to sort of dictate, that highest x exponent will sort of dictate what sort of shape it goes, or what kind of shape it will have. So we want to look for the highest one. Okay, now that I've found that, if I've identified the x with the highest exponent, leading coefficient is the number that will be right in front of that, which is 2. Okay, so that's my leading coefficient. This one just so happens to be arranged the way that we would like it to be arranged. It goes x to the 4, and then x. Okay. This one just so happens to be arranged in that way that we like, right? It's arranged in descending order. It goes x to the 4, x to the 3, and then constant. In the next one, you notice the terms are all, they're jumbled up, right? They're not arranged in descending order with the x exponent, so I would have to rearrange that to see properly, or I would have to just make sure I'm careful to see the leading coefficient and degree properly. Okay, but we'll get to that in a second. So what is the constant of this one? Is it Joey? Billy, sorry. It is -6, good. Okay, and then our basic shape is going to be based on whether our degree is even or odd. Oscar, do you have an answer for this one or a question? U-shaped. So this one is an even degree. It's an even number. So that means it will take on that U shape that we talked about with our power functions. Once I start adding other terms in here, like cubes and squares and stuff like this, it will take on maybe like a general U shape, but it might have a couple little twisties and turnies like inside there. If I start to add more terms in there, it changes the shape of the graph a little bit. But in general, it's always going to sort of follow that U shape. It will start up and end up, or down and down, or whatever. Okay? Okay, so I'm going to have you guys take a second and see if you can fill out this information for the next polynomial for part B here. All right, who can tell me what the degree would be here? Jessica? 11, very nice. Okay, so we mentioned this. This is not in descending order, right? If I were to put this in the correct, like technically mathematical order here, it would be this. If I want it in descending order of exponents. So the degree is not determined by whatever's first. The degree is determined by which one's the highest, right? So we just have to be mindful of that. Most of the time, it will be expressed to you in descending order anyways, but because we're just learning it, I jumbled it up a little bit just so we know that it's not always the first thing. So with that, what's our leading coefficient then? Sorry, Lucas. It's -1, yeah. So it's going to be the one, once I find the x with the highest exponent, it's always the one right in front of that, the number in front of that. If I just saw an x to the 11 and I don't see a number in front, what do I know about the coefficient that exists in front of just like a term like that, Nicole? It's a 1. So I would say the leading coefficient would be 1, even though I don't really see it there. Okay, what's the constant? Carol? 10, good. And the basic shape based on a degree 11. Victoria? S-shaped. Okay, because the degree is 11, which is odd, I know that this will take on an S shape based on what we talked about in our power functions above. Awesome. Okay, so this is connected, right? I'm always looking at my degree to decide on the basic shape, whether that's even or odd. Questions? Anything? We're all okay? Okay. Can I scroll? Okay. Okay. End behavior. So we're going to talk about end behavior and then turning points, and I don't know if we may be able to get to a couple, like one intro thing to our next lesson, but maybe not. So we'll see how we're doing for time, but probably we'll just wrap this up and then we'll have some time to work. Okay, so end behavior is essentially exactly what it says. It's how the ends are behaving. What are the ends doing? That's what end behavior is telling me. Okay, so it's a way of us stating how the ends of the polynomial or a power function that falls under that umbrella of polynomials behave. Okay, and really what I want to know when I talk about end behavior is like, where are they? And are they facing up or down? Okay, each of them. So there's two notations that we use for end behavior. And I'm just going to show you both of them. So one of them is quadrant notation. And the other is infinity notation. And for now, we will be practicing with both of these. I may, on a test or an assignment or whatever, quiz, I may ask you for a specific one, or I may just say, give me the end behavior in whichever method you feel comfortable with, okay? So I would expect you to be able to write both and also read both if I were to give you an expression and say, what is this telling me about the ends, okay? So quadrant notation, the first thing that we have to know for this is we have to remind ourselves what numbers each of the quadrants are. So this is quadrant 1, 2, 3, and 4 when we look at a graph. It's the same as how we number the quadrants, like we talked about the quadrants in like cast roll last year in grade 11. So same thing, it's 1, 2, 3, 4. And basically what we'll say is for both of these, we always usually start with the left end. We tell what the left end is doing, and then we'll end with the right end. So I'm just going to make a note in the middle here. We usually state both the notations. With left end behavior first, then right end behavior. Not as important in infinity notation. Like if you stated the right end first, that wouldn't be a huge deal, but in quadrant notation, we tend to go left to right. So I will say, in quadrant notation, when I am asked to state the end behavior, I will say quadrant blank. I fill that in, and this will be for the left end, to quadrant blank. So it will change based on what the graph is doing. And then I will state in this part what the right end is doing. Okay, and you don't need to put these, I'm just putting them for the sake of the formatting of this lesson for right now. Okay, so before we go to infinity notation, let's flip to the next page, and we're going to do this part, the quadrant notation, for x cubed. So just to remind you, x cubed, or y equals x cubed, maybe I should say, is that cubic function. It's a power function, and it looked like this. So if I'm stating quadrant notation here, remembering what each of these quadrants are, any guesses as to what I might say for quadrant notation? Quadrant blank to quadrant blank, if I'm going left to right. Oscar?
Quadrant 3 to quadrant 1.
Perfect. So for this one, I would say quadrant 3, which is where the left end is, right? This is down in quadrant 3. This is 1, 2, 3, or 3, 4. So I would say quadrant 3, which is where the left end is, to quadrant 1. Okay? Sometimes I have people ask me for this, like, what if my end, like, you guys don't have to draw this, but what if I have something like this? So this looks like it's maybe quadrant 3 to quadrant 1, but technically, because I have an arrow here, this continues into this quadrant, right? So you're always going to want to extend that graph. This is actually quadrant 2 to quadrant 1, okay? So this, I can extend it as much as I want, and this is always going to be in quadrants 1 and 3, right? This, I didn't extend it far enough, right? Because there's an arrow on there, so it keeps going. So just be mindful about that. Okay, let's do infinity notation here. So infinity notation, I'm going to draw a picture for this as well. It's like a little bit more complex, like the sentence, the mathematical sentence we write is a bit more complex, but don't try to complicate it in your head. So basically with infinity notation, I want to say what's happening on the left and what's happening on the right. And my answer is I'm always going to tell what's happening on the left and what's on the right by saying my graph is going up or my graph is going down on either side. Okay? The way that I say that is a bit more of like a mathematical, like formal way of saying it. But that's basically what I'm telling. Does it go up or down? We can all do that, right? We all can, I'm sure, recognize that. Okay, so if I go toward the left this way on the x-axis, would I be going toward negative infinity or positive infinity if I go toward the left? Negative infinity. So if I go toward the left, x would be going towards negative infinity. We say x approaches negative infinity. And that's how I'm going to express that I'm about to tell you the left end behavior. Okay? So I will start with as x approaches negative infinity. I will always have this because I'm always going to tell you what the left end is doing. Okay? And that is just saying as x goes toward the left, as we go to the left. And then I will state what the end is doing. I will state whether y is approaching positive infinity if my graph is facing up on that end, or I will state that y is approaching negative infinity. So if I put in infinity here, don't write that. If I put in infinity here, I'm saying that this end, as I go toward the left, is facing up, because this will be y is approaching infinity. If I put in negative infinity there, I'm saying that my left end is facing down, because this is where y approaches negative infinity, going down toward the negatives. Okay? So it seems complex, but really, the only thing I have to fill in is this space right here for both the left and right end. And I'm either putting up, which is positive infinity, or down, which is negative infinity. Okay? So you fill this in, this part right here. Fill it in with positive infinity if your graph is facing up, or you're going to fill it in with negative infinity if your arrow is facing down. Okay? And then the other part of this is I will tell what the right end is doing. So if I go this way on the x-axis, what is x heading toward? Is it heading toward positive infinity or negative infinity if I go toward the right on the x-axis? Positive infinity. So if I want to talk about what the right side of my graph is doing, I'm going to say as x approaches positive infinity, which will be the right end. Okay, again, these like bracketed things, you don't need these in your actual statement. I'm just putting it for the sake of our lesson right now. And then you will tell what that end is doing. So is the right end facing up, or is it facing down? If it's facing up, I will say y approaches. Okay, so if it's going up, I will say positive infinity. If my end is going down on the right, I will say negative infinity, as usual. So I will fill in again. I will say y approaches, and then I will again fill this in with infinity if my graph is heading upward, or I will fill it in with negative infinity if my graph is headed downward on the right side. Okay, so that's why I'm saying this looks complex, right? Like the sentences sort of look complex, but you only have to fill in one thing. You have to fill this in, and you have to fill this in. Everything else is always the same. And you will also obviously have to recognize that when we say x approaches negative infinity, we're talking about the left side of the graph. Okay, and then when x approaches infinity, or it goes toward the right side, that's the right end of the graph. Okay, and you tell me what it does. Does it go up on the right side? Does it go down on the right side? Does the left side go down? Whatever, right? It might be different based on what your graph is. So let's try it with, I'm going to erase these. Let's try it with y equals x cubed below. Is everyone good with the copying here?
Just a question, sorry.
Sure.
So it's x, y, would that refer to one individual line, or would it refer to different lines?
It will refer to the graph itself, but it's referring to two different ends.
Oh, okay.
So the first one refers to like what is the left side doing, and then the second one refers to what is the right side doing.
Okay.
But yeah, single graph. Yep. Okay, so let's try this with our x cubed. Oh, and this is frozen. That's why it's not letting me do anything. It's letting me do this. Oops. Okay, hold on one second. It's not letting me. Not really. My laptop? This cord too is not, sort of causes it.
Yeah, and then you had to like turn.
I know. Why? I think it is like partially the cord. Okay, there we go. That's not bad. Okay, so I already have it drawn for us here. That's going to be in the video now, so that's good. I already have it drawn sort of for us here. So this is not always going to be set up for you, right? You're going to have to write the full statement. But for now, this will always be here no matter what, right? I'm always going to say what is x doing as it goes toward negative infinity, and what is x doing as it goes toward positive. So I will always have these two things. And my job is just to say, okay, y is doing this, and y is doing this. So left end behavior, this one right here, imagine that you're just starting in the middle of the graph and tracing toward the left. What you fill in here is just whether your pencil is going up or down as you go toward the left. So if I start in the middle and I trace toward the left, what is our pencil doing as we do that? It's going down. So what should I say y approaches? Does it approach a positive or a negative if it's going down? Victoria? Negative. So I want to say negative infinity for this one, right? Because my graph on the left side is going down. Okay, so it's not that complex, right, when we really think about it. Okay, and then for the right side, I want to say, as I start in the middle of the graph here, and I go toward the right end, so that's as x approaches infinity because it goes this way, what does the right end do? Does it go up or does it go down? Up. So what do I want to say here? Athena? Y approaches positive infinity because my graph, my right end is going up. Okay? So that's essentially what I'm saying, right? As I go toward the right, I'm going up, and as I go toward the left from the center, I'm going down. Okay, so don't complicate it in your mind. I know that like this looks kind of weird because we're using all these different infinities and stuff, but it's really just like, tell me if it goes up or down. That's it. Okay, so we've got one last little thing here, and then we'll have a little bit of time to work today. The last term that we're going to talk about today, or the last new thing, is called a turning point. So turning points, whoops, there we go, keep that there. Turning points are any point where your graph changes from increasing to decreasing or decreasing to increasing. They will form mountains and valleys, and they'll be like the tips or the peaks or bottoms of those. Okay, so any point on a graph where you go from increasing to decreasing, okay, and what that would do is it would form like a mountain, right? It would go up and then down, and that would be your turning point right in the middle of that. Or vice versa, right? Or decreasing to increasing. And that would basically be decreasing to increasing, so it would form like a valley. And the very in between of that, the bottom of that valley would be your turning point. It must change from decreasing to increasing or increasing to decreasing. If there's any little dips or anything like that where it still is continually increasing or continually decreasing, that's not going to be a turning point. Okay, so the next example is a good visual of that. So in this question, we want to state how many turning points does this function have? And we're also going to state the end behavior in both notations. So we already know end behavior. Let's just do that quickly. And we're going to imagine there's arrows on the end of this. So let's start with end behavior, and then we'll talk about turning points. Okay. Who can tell me what the end behavior is of this graph in quadrant notation? Carol? 2 to 1, perfect. So if this is quadrant 1, 2, 3, 4, Yes, it travels through 3 and 4, I see that, but the left end is in quadrant 2, and the right end ends in quadrant 1. No matter how far I extend them, right? They're always going to be in those 2 quadrants. So we will say quadrant 2 to quadrant 1. Sometimes, like eventually, I'll just be like Q2 to Q1. That's fine, as long as you know what that means. Okay, so that's quadrant notation. Let's talk about infinity notation here. Okay, this one's not pre-written for us, right? We had pieces that were pre-written for us in the previous example. Now we're going to do the whole statement all together with the x's and the y's here. So does anyone feel confident that they could state infinity notation for this one? Or just want to put yourself out there to kind of guess? Mathushini? And you want to do the second part? Very nice. Okay, so I must have, no matter what, I must have these 2 pieces. I will always have an left side as x approaches negative infinity and as x approaches positive infinity. Those are always the same. These might be different depending on what the left and right ends do.
Do you want us to like label them saying like quadrant 1 and 2, so or 2 is just implicit in like the explanation for infinity notation?
No, you don't have to say anything about the quadrants here. It would be understood based on what we're saying. Because if x is going toward the left and y is going toward infinity, it's going to end up in that quadrant anyways. Yeah. So if you're doing infinity notation, you wouldn't have to do anything with the numbers of quadrants. So any questions on this, on why we decided on any of these? Can someone just explain to me quickly why Mathushini chose these 2 things here? Oscar?
Because both endpoints, they're both pointing up, which is towards positive infinity.
Okay. So the left end is facing up, which is toward positive infinity. The right end is facing up, which is toward positive infinity as well. So they have the same upward facing and behavior. Questions on that? We're all okay? Okay. Turning points. Any guesses, now that we know the definition of turning points here, any thoughts on how many turning points would be on this graph? Okay, this one's maybe like a little tricky because we've got a couple little squiggles in here. Athena, what do you think? Okay, Athena's thought is 3. Carol, you agree? 3 or maybe 5. Billy, what did you think? 3. Victoria? 3. Consensus seems to be 3. You guys are right. So it is 3. So there's one here. We change from decreasing to increasing. And then there's one here. We change from increasing to decreasing there. There's another one right here. We change from decreasing to increasing. This one it sort of like tapers out, but we never get that like mountain or that valley that happens there, right? It's sort of like always increasing on this slope here. Oscar? Exactly. Yeah. So yeah, we would say 3 turning points for this. Okay, and maybe I'll just highlight each of those turning points there. Okay, any final questions here for anything on this lesson? Okay, let's pause this.